Let's look further at the development of the nuclear model of the atom. So Thomson is where we left off with the plum pudding model, with the idea that negative electrons exist within a ball of positive charge, and the idea is that positive charge is that dough that kind of holds it together. Well, it didn't take long before it was shown that this plum pudding model was not sufficient. So in 1911, Ernest Rutherford did some really neat experiments. He placed a sheet of gold foil in front of a beam of alpha particles. Those alpha particles hit that really tiny thin sheet of gold foil, and he expected the alpha particles to just pass right through the gold foil. But that's not what happened. The alpha rays started bouncing around and deflecting at all different angles, being picked up by the detector that was all around the gold foil. And basically, this is a huge surprise, because if it's only this blob of positive spheres and there's nothing that's dense or hard in the center of that, plum pudding model, then it should have passed through. He said it's like if you fired a 15-inch shell at a sheet of tissue paper and that bullet came back and hit you in the face. That wouldn't happen. You would be very shocked. Same thing with Ernest Rutherford. He was extremely shocked. And so what he realizes from this experiment, there must be something dense and tiny right in the middle of this atomic space. And so with that, he was able to propose the nuclear model. He expected it to work like the plum pudding model, but that's not what he saw. And so even now, he knew there had to be a nucleus. He didn't know about that proton yet, but he knew there had to be something very dense in the middle that was deflecting those alpha particles. So now let's think about whether or not the nucleus could be composed entirely of protons. So James Chadwick proposed that there had to be something else holding that nucleus together, because protons are positive. So if you have 2 or 3 protons together, they should repel. But the nucleus doesn't just fall apart. Instead, you have these neutrons that are in there intermixed within the protons, kind of like a glue, forcing these positive species to be in close proximity to each other. These developments contributed to the nuclear theory of an atom, and so this is our nuclear theory that we hold for today. First, most of an atom's mass and all of its positive charge are in the core, the nucleus. So electrons are very, very small and tiny, and their mass is about 2,000th really of the other particles. It's very small in comparison, and it's positive because it's got neutrons and protons on it. The second tenet is that most of the atom's volume is empty space, and through which this empty space, negative electrons are dispersed. And so think about it, if you look up at the sky at night, you see stars. Stars obviously don't make up the majority of the space, but when we think of space, we think of all the things that are in it. We don't think about the negative space. That's how an atom is. Most of the volume, if you just touch part of an atom, you probably touched empty space, but the negative electrons are dispersed throughout it. And then the last one, negatively charged electrons are equal in number to positively charged protons if the atom is neutral. And that makes sense, because if you have a +1 charge for a proton and a -1 charge for an electron, they're going to balance each other out, making it neutral. So let's talk more about this periodic table. The periodic table is really our cheat sheet in chemistry. I can't imagine doing chemistry without it. Here you can see the main components, where we see our atomic number is written right above the elemental symbol, and then the average atomic mass is below that, and then underneath that we've got the name of the element. So how we can look at this then is a couple different ways. We have our mass number and our atomic number and our elemental symbol. So these two forms of writing the elements can go back and forth between each other. So what you see on the left is what you find in the periodic table, and on the right is if you're trying to represent the element or represent isotopes in particular, you will see this. So how do they go back and forth? So this atomic number is Z. Here, that's always equal to the number of protons. Always. If you change this atomic number, you're changing it to a different element. You're turning into an alchemist. If an atom is neutral, then this number is also equal to the number of electrons. If it's not neutral, then those two are not the same. Protons do not equal electrons if the atom is charged in any way, either positive or negative. This mass number here is your number of protons plus your number of neutrons. Remember, electrons are tiny. They barely contribute to the weight of an element or an atom. And so therefore the mass number, that atomic weight, if you will, that mass number is the combination of protons plus neutrons. So if you know the atomic number and you know the mass number, its mass, you can simply take mass number minus the atomic number and tell yourself how many neutrons you have. All right, so review. Can you name the 3 subatomic particles in an atom and list their charge? Hopefully you said proton, neutron, and electron, positive, neutral, and negative. What number on the periodic table tells us the number of protons in an atom or element? That is the number that is right above the elemental symbol, your atomic number. If an atom is neutral, how are the protons related to the number of electrons? Hopefully you said they are equal. Alright, so now let's do some more practicing. So if I ask you the question, what is the average molar mass of each of the elements shown below? So meaning, what's hydrogen's average molar mass? You would say 1.00794. And that is if you're talking about one individual atom, AMU, or if you're talking about it as a property, it's 1.00794 grams per mole. Okay, for carbon, 12.0107 grams per mole. All of these numbers below the element, those are the average molar masses. All right, so I want us to work on identifying how many of each subatomic particle exists within a given atom. So for instance, with fluorine, here you can see fluorine's what the information is given to you on your periodic table. I do recommend printing off a periodic table at this point and keep it in front of you. You're going to use it really for the rest of this course. It's going to be a very vital part, and you can write all over it, write down anything you need to help yourself remember what do all the pieces mean. So in this case, what is my approximate atomic mass? We've got our elemental symbol, and then here we have our average atomic mass. And then at the top we have our atomic number, which remember also equals the number of protons. So in this case, we are going to be able to use this right here, the mass number, the atomic number, the elemental symbol, to fill in this chart. So approximate atomic mass. I did this because we haven't talked about isotopes yet, and so we are just going to approximate it. So meaning if you have 18.998, we're just going to approximate it at 19. Okay, but then we're going to be able to use that number for filling in the rest of the chart. So approximate atomic mass in this case is going to be 19. Because that's what it approximately weighs. My atomic number, that's going to be 9. That is from up here. Then we have 9 protons, because remember, atomic number equals the number of protons. Then 10. How did I get 10? Well, if this mass number here, or the approximate molar mass is 19, and I know I have 19 protons, I can take 19 minus 9 to give me 10. Okay. Then number of electrons is number of protons if it's neutral. So if it's neutral, those two should be the same. Double check by yourself by saying protons plus neutrons should equal the total weight of the atom, which they do. Let's do another one. Carbon. So what is my approximate atomic mass? Hopefully you said 12. Then my atomic number would be 6. Protons equals atomic number, and then neutrons is 12 minus 6 gives me 6, and if it's neutral, it's the number of electrons equals the number of protons. And you would represent it chemically by this. Now, I do want to note that why does the atomic mass say it's bigger than 12? If I have 6 protons and 6 neutrons, shouldn't it weigh 12? Well, we're going to learn a lot more about isotopes later, but the idea is an isotope is anything that has the same number of protons but a different number of neutrons. So if we add a neutron to it, then we're going to just be changing only one thing, and that thing that we're changing is the mass. And so some carbon atoms exist naturally in nature, that's kind of redundant, with a different number of neutrons. They all have the exact same number of protons. That's why this bottom number is the same. Remember, this bottom number correlates with the element, so the bottom number never changes, but the top number can change depending on which isotopic form you're looking at. And so in this case with carbon, there are more carbon 12s in nature than there are carbon 13s. That's why the average mass that you see here of 12.0107 is closer to 12 than it is to 13. That just simply means, hey, there's more carbon 12 in nature than there is carbon 13. So I want you to practice. Go ahead and stop your recording right now and try and fill in this chart and see how you do. What you should get is all of these numbers. The idea of oxygen weighs about 16, therefore it has 8 protons, 8 neutrons, 8 electrons. Magnesium, more of the same. It weighs about 24, which means it has 12 protons, 12 neutrons. Bromine, now you're getting to be bigger numbers. The larger you are, the more positive charges you have shoved in that nucleus, which means you're going to need a whole lot more neutrons to hold it together. And that's what you see here. 35 plus 45, your mass of your protons plus your neutrons equals your mass of your element, of your atom. And then your electrons still equal your protons. Same for gold. A lot more neutrons are being needed. And so now we've got 79 plus 118 gives me a total mass of 197. Helium, pretty simple and straightforward. Cesium, also a little bit big, so it needs a lot more neutrons. But hopefully you should be able to fill in this chart. Okay. Now, let's practice some more. I want you to come up now with the symbol form for it. So meaning up here is going to be your average mass, your element, and your number of protons. So give it a try. And you should get these things. So go ahead and pause it. Try it on your own. Then check your work and see how you did. Alright, so to kind of summarize, if you take an atom and you add or subtract a proton, it's becoming a new element. So you can't change that atomic number. If you change the atomic number by changing the number of protons that it has, you're turning into a new element. So that's alchemy. We don't do that. Okay. You can do that when you're talking about splitting the nucleus and like nuclear fission, but we're not getting into that in this, really this course. Okay. You might get into it in the second semester. If you take one atom and you add another atom to it, that's called a molecule. If you take an atom and you remove an electron or you add an electron, it turns it into an ion. And if you take an atom and you add or subtract a neutron, it's now called an isotope. Alright, so now go read section 3.6 through 3.8 and we will continue on.